third lecture of Dr. Sayed on dynamical system perspective with stochastic differential.
Okay. Good. So, the last two lectures, first I did a very simple example of a random system only built of convections. And the advantage of that was that it was more or less exactly solvable at the level. So, and then you could see all the concepts. Then yesterday's lecture, we looked at a simple dynamical system, random composition of circle homomorphisms, still not so easy, but at least the underlying structure was not so complicated. It was also still an iterative function system in the sense that we just pick transformations from a given set and we have a discrete time, so it's kind of easy to see how we update it. Today I'd like to talk about some examples of random dynamical systems that come from differential equations. And one of the questions actually is to what extent the stochastic differential equation does generate random dynamical systems. So if people think about stochastic dynamics or stochastic evolution, then most mathematicians and maybe also most people in applications would think that you have to write down a stochastic differential equation. And of course, this is one way to model it. I would say the models that we saw before, like have a discrete time operator with some noise or with some bounded noise or a parameter noise, so of course also an option. But the stochastic differential equations are quite popular models for several reasons, not in the least because people developed a way to do calculus with the differential equations, and we could solve particular type of problems, so that it's a motivation. I think that there's a certain kind of question of to what extent random things should be modeled by stochastic differential equations or with which kind of stochastic differential equations, but that's not the aim of the lecture. The aim of the lecture here is to basically provide some kind of entry point of so how can we look at stochastic differential equation as a random dynamical system, and then what kind of consequences would this have for how we look at this. So it should maybe be emphasized the stochastic differential equation by itself is not really a random dynamical system. So we have to some kind of provide some kind of perspective to the stochastic differential equation so that we can think of it as a random dynamical system. And the random dynamical system, as I introduced before, is like a co-cycle. So we have some model of the noise, and the noise drives the dynamics in a non-autonomous way. And the stochastic differential equation is a different object. It is a relationship between variables in a certain way, and it's actually more defined in terms of its integrals than in the integration properties than actually in terms of like designing solution paths. So in the stochastic differential equation, it's not necessarily clear that there is a solution path. Although of course you can compute expectation values over events and so on as a stochastic process. But anyway, there is of course close connection. So what we can do is we can look at stochastic differential equation and add some structure to it, which doesn't make it anything more special than it is. It just makes it more concrete, and it stays within the context of stochastic differential equation. And then the model when we look at looks more like the random dynamical system that we're used to. And so a similar aspect maybe is when we looked at the random composition of iterative function systems. So in the beginning or in the first lecture or yesterday, of course also I have some kind of vague process. Then I replace this process, the noise, I make it very concrete. I say, oh, coin tossing is actually a symbol sequence, and I have a shift operator and have all these other things. You could say, that wasn't there before, there was only a story. But then I make it very concrete. So in the stochastic differential equation, we can do similar things. We can build a model of the noise which is completely consistent with what the stochastic differential equation is supposed to do. And then suddenly we have a way of looking at it in a more dynamical systems way. Okay, so that's the kind of the idea. And so the problem maybe with stochastic differential equation is that stochastic calculus is not so trivial. So for many people, this is a reason not to do stochastic dynamics. Whereas maybe if you do iteration of one-dimensional maps, everyone can understand in 5 minutes if you have high school mathematics what the idea is. And if you write down stochastic differential equation, it's a little bit harder. Maybe in Japan, hopefully people learn properly stochastic calculus and everything. Because of course it's a great addition in this country. But in general, I would say why this area is maybe not so much penetrated as it should be is probably because there's a perceived technicality to it, which maybe is not necessary. So yesterday and the day before we did random systems where we didn't really do stochastic differential equations, and it's not clear to me that stochastic differential equation per se is better or worse. I think it just depends what you want to model, what is the best way to go about it. Anyway, that's introduction. So I'd like to talk about stochastic differential equations generating random dynamical system. So what we need to kind of come to grips with is some kind of like model of the noise. And so the model of the noise for stochastic differential equations is a Brownian motion. And this is characterized by these properties. Brownian motion is described by a Wiener process, and it has some properties that at zero, it's zero, it's almost surely continuous, there's independent increments, and there's some independence in different variables. So we have some kind of like graph, and then we have a certain distribution, normal distribution, Gaussian distribution here for these things. So this is basically the setting. We assume that the noise has a certain property of this kind, and so so of course this you want to kind of build in. So we want to build a model of the noise that has these properties. And so here is some example of what noise could look like with these things. So you start with the point 0 and it evolves in a certain way. And of course, many things are known about what Brownian motions are and what they are not. Like they are not supposed to be differentiable and things like that. And so there's a lot of consequences from the properties, a lot of consequences come from that makes it non-trivial. Now the question is, how can we build a model that actually takes this kind of Brownian motion into account? Well, there's a certain suggestion here that if you look at these curves, they look at these like kind of continuous graphs. So the idea is to somehow to start from continuous graphs of functions and try to derive from that a probabilistic model that has the right statistics, and then use that as an input for the stochastic differential equation. So here's the idea. So we take a function space of continuous functions here from the on the positive half line for input into R, and with the condition that there's 0 at 0, and we introduce some kind of metric. Of course, this is kind of a trick to do these things properly, so that we can compare these functions with each other. And so this is some kind of you can see that if the curves are close to each other, they basically are they're almost the same curve. And there's of course some weight here in the end. Okay. Now there exists a Wiener measure on this space, such that we precisely have kind of the right statistics. So what you want for this Wiener process is that this kind of statistics. This is the important thing. So the trick here is to, when you start with the continuous functions, not necessarily okay, but you want to kind of build the model in such a way that we have a measure that is consistent with what we want from the noise. And what we want from the noise is the following property: is that the probability to have a certain property here of this variable being smaller than x, that the distribution is given by this Gaussian curve. Yeah? Okay, then we also have independent increments in that setting. And then what we end up with is a probability space that is constructed in this way from these functions, and it's canonical central path of Brownian motion. Okay, this is a very quick thing, but we think of this this sense in this way. So we define these measures. so now we want to get a model of how then time evolves on the noise. And so time evolves on the noise in this natural way. So we take a function, this is my continuous function, and I let t operate, and what I do is I shift forward, but I also can reset the curve somehow. So I have a graph. So I write my zero being affected the curve, I don't know what it's doing. Some continuous function that is generated. But this is t. And then at some point we sample it somehow. So we read it up in the value of t. And so as soon as we sample it somehow, what we do is we reset the signal. It's a bit the same thing as when we have a symbol sequence of events. As soon as I read the symbol, I just shift the thing back to initial condition. So what we do is we shift this guy basically to here, shift the whole graph back to here, and we go further. And so of course what we can do is we can read this graph at any point we like. But it's important that we do that. So that's the time operator. So the time shift operator on the space is precisely that. We read the curve, we read the values, and we then reset. Okay, this thing can also be upset. Now the nice thing is that this operator is ergodic flow, precisely preserving this probability measure, the Wiener probability measure. So this is of course a bit of an art, how to set the things up in such a way that they precisely have the right properties. But this has been done. Okay, so instead of having some kind of like abstract idea of what the probability should be, which is stochastic calculus, you would actually have the understanding of what certain integrals would give. Is here we kind of build a model of the noise that in some kind of very concrete way also has its properties. Just by setting it up, so setting the base row up in a certain way so that it generates precisely the right properties for the noise. And then we can basically build a dynamical system. What do I do? We take this base flow and we take this signal that comes out of it, basically as the input of a differential equation. Okay, so how can we try to start doing that? We go from the stochastic differential equation to the random system. Let's look at the simplest type, which doesn't give so much trouble, is this differential equation. There should be a dt here. So the dx is f of x dt plus sigma dwt. So dwt is somehow the derivative of this Wiener process. But we can, in this simple version, we can integrate, because the noise is completely separated and it doesn't depend on anything. So we can actually write the integral version of this equation in the following way. So we can write xt of omega is x plus sort of dx s of omega ds plus sigma wt. Wt is just this curve. So if I take a realization of the noise, okay? Yeah. Good. So if you take a realization of the noise, then we have this implicit form of the solution, but this looks very much like a Poincaré iteration, and this can be solved. And so basically, there's no problem here with the existence and uniqueness of these kind of solutions. So this provides a very nice setup. So we know basically how to find solutions of these equations in terms of this integral equation. And we don't really need too much other things here. Yeah, so the models that we look at today will basically be mostly be of this form. This is the simplest form of adding some noise to something. And why look at these models? Because I'm trying to do as easy as possible models for a random dynamical system, but it's not necessarily restricted to this. Because of course there's also famous Japanese mathematician that most of you will know, that build understanding of how to solve equations in general, stochastic differential equations. And of course, then it's not always so easy to do this. So we can write formally something when we have some issue with solving such integral, and then we will need Kyoto calculus to understand how to do this. But there's people from this school in Bremen, from Bldg Arnold, in this book, which I've flagged up a few times, have worked very hard to make sense of the fact that in some way or another, also in this case, you can actually make sense of the stochastic differential equation as a random dynamical system. But there's some technicalities there which are less trivial. So I will not go into that, but be assured that with an SDE, one should be able to find an appropriate random dynamical system formulation of the model. So I think the nice things about having a dynamical formulation of the model is that we can then think about the dynamics. There's a certain issue with if we have a differential equation where we don't really necessarily define solution paths per se, that the concept of dynamics is more abstract. We can then look at the consequences of dynamics. And it's kind of very useful, I think, also in classical mechanics and in, the whole development, I think, of differential equations, of modeling of dynamics. It's actually, the idea was to make a mixture between analysis, which I think is like solving differential equations. Yeah, this is a question like, so does there exist functions that solve a certain equation? To Poincaré's view, where maybe we have a geometric picture of what's going on, and we can actually lean on other type of mathematical knowledge to try to understand our system. For instance, if you look at the ODEs, of course the ODE theory is like, can we find a function so that some differential satisfies some other thing? And one can do that in a very analytical way, and one can of course get fantastic results, but really a lot of breakthrough came from the fact that when one found out that you can't really normally solve this by quadratures or something like that, or cannot solve or by standard functions or something, that you can say, like, what can we say about solutions to differential equations? And the geometric methodology gave a completely different point of view. It didn't give you exact solutions, but it gives you properties of the flow and insights of what the dynamics does at a completely different level. You could say, okay, if I don't get the exact numbers or the exact functions, I'm not happy. But actually, by systems where you should not be expected to find this, you could still get a lot of like qualitative properties. And so people call this geometric theory of ordinary differential equations. And that's a very big success story. I think that in some sense, geometric theory for stochastic differential equations is just not as developed. And this is just the random dynamical system point of view is an attempt to build a more geometric point of view. Although, of course, we can also look at it at an analytical point, but there is this geometric opportunity, because when we have solution curves, we can try to compare solution curves, and we then think about, like, why do things happen, what are they just conclude that they happen. Okay, good. So the question is, like, how can we see that there is a co-cycle? So we can write down solution, and then we can, from the integral equation, make an observation that we can write this equation this way. So this is just basically following the associated equation. Of course, it's still implicit. And then we can check that the co-cycle property works. So we have these properties. If I subtract these two, I get this equation. And then by the uniqueness of solution, we can check that in fact this co-cycle property holds. So this is the usual co-cycle property that if I flow by T plus S, it's the same as flowing first by S, then I flow by T, but I have to shift on the base appropriately. This is just a usual co-cycle flow. And so this is it follows directly from the integral form of the solution in an implicit way, and by uniqueness, that we can just get the co-cycle property. Okay, so in the case of additive noise, as we call it, then somehow it's rather straightforward to see that we have a random dynamical system, and so we can basically take everything we know from before with our model of the noise and try to kind of do random dynamics for such a differential equation. Okay, so this was the idea somehow to basically set up and to say, like, look, even if you write down a stochastic differential equation, which doesn't look immediately like a co-cycle, but the other form looks more prettily, that we can think of the stochastic differential equation as a co-cycle with the given model of the noise and understanding the looping. And I made it clear that in the case of additive noise, this is actually quite constructive, so you don't really need to do very deep things here. So the next thing that I like to do is to look at some examples. In some sense, the course is full of examples to just get a feel of what's going on. It's not only that the examples are there to get a feel, but also because there is a lack of big theories that actually tell you things that are not can be seen in the examples. So, okay, so we look at a simple model of an ODE first, and it has a bifurcation property. So here we have x dot is alpha x minus x, and so what is ODE? It's ODE on the line. So we have here a flow on the line, and so what is it? If alpha is negative, then we have a unique solution, a unique equilibrium solution in 0, and the flow just goes from all directions into 0. If alpha is positive, then we have, maybe should not the other way around. This is 0. If alpha is positive, I have 3 solutions. This is plus or minus square root of alpha. And then these guys are stable. This is unstable. But so there's a, and at alpha 0 there's a branching point. The branching point here, so they have a unique solution 0 here. It becomes unstable about stable branch goes here and have an unstable branch there. And because this thing looks like something like a pitchfork, this is something you use on a farm. You pick up the hay and throw it to the animals. So it's called pitchfork bifurcation. So we have this very simple ODE, and there's no mystery about anything here so far. So we know everything. I hope you agree that you know everything about this ODE. It's a simple ODE. I want to know where you have things that attracting two attractors that one repeller here that have a unique attracting point. It is called bifurcation point. Just to go from a situation where I have only one attracting point to 2 attracting points. And bifurcation also basically comes from this picture in some sense. Because we go 2 ways by bifurcation. Good, very classical. And now the question is like, what happens if I add some noise? Right? So we know how to do that because we just shown it. So we take some sample path of the noise, and here there's some numerics of what you see. So here the 3 situations. So what do I plot here? I notice that the differential equation x dot is alpha x minus x to the third. And this thing is the differential of a potential. It's actually v prime of x, where this guy is alpha divided by 2 So this is some kind of like potential. It's actually gradient flow for this potential. So if I take this as a landscape, then the differential equation basically says I just flow down the hill of this landscape. It's a gradient flow. So if I plot here the pictures of this V, then it gives you some kind of idea of what's going on. And so it's basically, if you're on the top, you just tend to fall down, and if you're at the bottom, you will stay there. That's basically what this differential equation does. But I have, of course, this noise term. So what's basically, so this is the different situations. Alpha is negative, alpha is 0, and alpha is positive. So you see the bifurcation, because here we have unique minimum. Then this unique minimum flattens out, and I get two minima and a maxima in the middle. And this is just a naive computation. You take an orbit with a certain noise intensity. I don't know exactly what it is, but it's reasonably large because we reach. Of course, it's stochastic, so it will smear out, but it's reasonably broad. And what you see is you just do a histogram of where the point is. Okay? So you just run it, and you see what happens. And I think I have some videos in me. Look. Okay, you see a picture of this thing sitting there. No surprise. If you sit in the bottom and you shake it a little bit, it just shakes around in the bottom. Right? And so the histogram that was plotted was just basically plot where the point is and just count where it is and plot the histogram. You have some distribution. Okay, this is done. And the next movie that I'd like to show is after bifurcation. You see here. But you see that what happens that after the bifurcation, through the noise, it could go from the right to the left. It can actually jump. So if you have no noise, of course, then we just have two equilibria. You sit either on the left hand side or the right hand side. It can never go from the left to the right. It's impossible. There's an obstruction here by an unstable orbit, and it will just basically push you away. But in this case, through the noise, we can overcome this barrier. You see, but there we go. It just flips over the barrier through the noise. So you see also something nice here, which maybe I should emphasize, that noise can model something more complex than an ODE. Because if you think of something, in order to get another model that has this kind of behavior, I have to go like a high-dimensional model that has such features. And in some kind of compact way, in a stochastic model, we can get very complicated behavior. Like, for instance, how does something simple interact with the rest of the world? Something that is complicated through stochastic differential equation, and I get a comprehensible picture. So there, in a deterministic system, it would be very difficult to somehow understand what kind of equations you have to write down to get precisely to this kind of thing. You would set it up, of course, as the driven system, but as a noise is a nice way to modify the idea. So we have, for instance, this double well, and then I have some noise and something. Okay. Good. Okay, so we like to kind of basically carry out some program that is similar to what we did yesterday, to just try to understand what's actually happening in the speech, for example. And so we'll look at these aspects: stationary distribution, depth correspondent, pullback measure, pullback attractor, synchronization. I hope you are slightly familiar now with these terms, and we can see what we can do about them. So first, the stationary measure. So the stationary measure of the stochastic differential equation can be derived as a solution of the Fokker-Planck equation. So the Fokker-Planck equation, the derivation is on page, and maybe I've seen it before. So P is the density, we talk about the back density. So we talk about measures. So that d mu of x is dx dx. So we go from the measure, sorry, let me go rho. So we look for a stationary measure, or a measure, rho, and I write it as the back density. And also maybe yesterday wrote lambda x. And so if it's absolutely continuous with respect to the back measure, so it means that we have basically corresponds to null sets for both, then I can write it in this way, we have a density. Yeah. So the Fokker-Planck equation is basically the Markov operator on measures, but in the density form. Right? So this so for this specific equation, there's a recipe of how to get this equation. And so for the specific equation, the push forward of the density is precisely given by this equation. So there's the different parts of the differential equations come in here. There's a noise term here. This is the diffusion term coming from the Brownian motion. And so the derivation is going to use this some eco formula here for the diffusion. So I assume that you've all seen it sometimes. And otherwise, it's a short exercise. Okay, so this is the kind of the Markov process for the density. And the nice thing here for this example, as in many one-dimensional examples, is actually quite easy. So Fokker-Planck equations are horrible at high dimensions where they're really important, but when they're not important, then they're easy. So we can try to solve for the stationary measure so that the thing here doesn't depend on t, so the left-hand side equal to 0. And that's easy enough because you see that we have a derivative here, so we can create a constant here, and then we can solve immediately with this condition to get a probability measure, is that we get this exponential of this potential, basically, with a prefactor of the strength of the noise, and that's a normalization factor, just to make sure that this guy equals to 1. Doesn't matter so much, actually what it is, it's a constant, depending on sigma and alpha. So you can compare this, so what does this thing look like? Well, roughly you can see that it depends on the sign of alpha. So this is a quartic potential, which has basically, with alpha smaller than 0, has like this shape. It's not that if alpha is bigger than 0, precisely this shape. And if I then take this exponential of it, I get precisely this kind of distribution that before you get something which has 1 hump, or you get something which has a double hump of some kind. And this, of course, corresponds quite well with what we saw here. We have like a 1 hump solution. It's actually a especially flat solution where the alpha 0, we have no quadratic term in this exponential, and we get basically another type of distribution this time. So I didn't check here that these graphs with a numerically obtained are exactly this formula, but it better be. Okay, so why do I show this? Because so for most people doing stochastic dynamics, or say statistical mechanics community or something like that, when you get to a Bifurcation bifurcation and we add some noise, this is exactly what they will do. They say, Fokker-Planck equation. They go Fokker-Planck equation. Say, Fokker-Planck equation we can do. Then we solve Fokker-Planck equation. End of story. Finished. They go home. They say, problem solved. Actually, trivials and textbooks you find everywhere. But it doesn't say anything about dynamics. It says something about this distribution of statistics, if it's also ergodic and so on, which it will be. And it says, of course, like if I say, well, what's the chance to arrive in a certain part of the phase space? This solution will tell you exactly. But it didn't tell you how you got there. It didn't tell you how often you come back. It didn't tell you if you have other trajectories, what they will do with respect to each other. So it doesn't do any dynamics. It just do really statistics. Right. So this is interesting in some sense. So if I was from a different school, I would just stop here and say that it's actually boring, and I should never talk about this example. But I will talk a little while longer about this example because it turns out to be much more interesting than you maybe would immediately think. Okay, we can also do the outcome exponent. It's another nice feature. So the outcome exponent can also be computed explicitly, because we know the distribution explicitly. So what is it in one dimension of the outcome exponent? The outcome exponent is the process here of the flow, for the time t flow, which is actually precisely the same if you know the distribution of the trajectory, because the derivatives commute. It's basically just the integral, it's just the vehicle integral of the invariant measure, which is here in terms of the density of the derivative. Now, in our vector field, the derivative is very easy because the noise doesn't appear. Right? So we just get basically the first term, which is the derivative of vector field, the dx, that's noise doesn't depend on x. And then this is just a distribution, and you can just, by one-time partial integration, you can see that this is a term which is positive here, positive there, negative 3 factors, so this is actually strictly negative. Right, so we can actually analytically show that for this example, we have negative Jakob exponent. Now the interesting thing is, this is completely independent of the value of alpha. So let's go back to this picture. When we had the deterministic picture, I had a negative Jakob exponent here. Of course, also here, but I also have some repulsive things. So I also have some kind of omega limit set or a repeller point, which also has an ergodic measure somehow, just on this point. It's repelling, but it has a positive Jakob exponent. So you have here a mixed picture with two sets. That in the random picture, it just have one invariant measure, one stationary measure, and the stationary measure carries a negative Jakob exponent. That's consistent with what we saw yesterday. In the one-dimensional case, we should somehow expect negative Jakob exponent. Of course, there's a certain issue here that we are not in a compact space, but we saw already that we have a solution to the Fokker-Planck equation, so we just know we have stationary distribution, so that's not an issue. And we have this negative thing. So what do we expect with negative Jakob exponent? Well, hopefully with some good conditions, maybe we have some synchronization, maybe we have contraction towards one point. But the nice thing is that so far, everything we did was just analytical. And so in order to prove these things, existence of the tractor in general, we need to look at the absorber domain, because we have this kind of non-compact space. So in order to prove that you actually have a random attractor, you now have to kind of do some procedure, and we'll look at it a little bit more carefully a little bit later when I do a similar model, where say something more about the details. But the basic idea is that we look in an unbounded domain, non-compact case, for so-called, we look for the invariant set, of course, where we get attracted to. This is a random attractor. And in order to prove that we such have a random attractor, I'm looking first for a compact absorbing set. There's like some kind of basin of attraction. And so in deterministic systems, I might be interested to, if I have an unbounded system, to see if everything ends up in some bounded region. And then I have a compact system and say I can't leave that, then I know that everything behaves like in a controlled way. But you always have to be careful with, if you have a non-compact phase space, is that dynamics could just fly to infinity. And then there's not much to say. And so this is not good. So many theories about dynamics or attractors assume compactness of phase space somehow, and if it's not compact, then we have to always be a little bit worried about the fact that maybe things fly away. But if you have an absorbing set, that means that everything has, after some time, and this is here in compact sense, of some time, you end up in some kind of given compact set. Now, in this case, it's so that this compact set also depends on the realization of the noise. So the compact set here, the absorbing domain, is a random absorbing domain. It's one that depends on the noise. So it looks a bit abstract, and you say like, well, how could I ever find out if this was the case? And good news is that there are techniques for which you can actually, for certain class of equations like this, stochastic differential equations, you can actually control this. And the basic idea here is a little bit that if you have this this kind of potential, if the potential is steep enough, what happens is that you can actually, it gets contracted towards the origin relatively fast, and the diffusion is relatively slow in comparison, which gives you the fact that you on average actually are contracted into some region which is compact after some time. But there's some techniques for that, and I will kind of mention a little bit about that a little bit later. But given such a compact absorbing set, then you can look at some omega limit set. This is the definition of omega limit set in the set sense. So we take some set, and set B, we look at this pullback omega limit set, with the things where you accumulate to, and this is that this exists in a compact setting, and then is the attractor. So this picture, for example, has a random absorbing set because it has good conditions at infinity. It gets strongly pulled in from the outside. Okay, so if we know that this thing exists, then we can actually look for this pullback object, because otherwise we might not entirely know that it exists. And so here we have it. So for all alpha, we have a pullback attractor, and this pullback attractor is actually a delta measure. And so the proof proposed that we have we have fibers on which this attractor lives, and the problem is that you can have intervals. But if you have interval, you have a unique stationary measure. This gives you a unique pullback attractor. But if we had not a point attractor, but it had to be an interval. If it was an interval, then also the endpoints you have a pullback attractor, and then would have no uniqueness. So by uniqueness of the pullback attractor, it must be an atom. That's the reason. So if you have a pullback attractor, this from this set, it converts to something. If it's not a point, it will be an interval. If it was an interval, then at the endpoint, you would also have these also will be pullback attractors, and then there would get no uniqueness. So because of uniqueness, we have atomic pullback attractors. That's the idea. Anyway, but it looks very similar to a situation we had before. And importantly, so this doesn't depend on the value of alpha. Right? It depends on whether it's strict on the noise. But for any value of the noise, we have this result. So if you believe that the dynamics is completely described by pullback object or a pullback attractor, synchronization, then we are somehow in trouble, philosophical trouble. Because when at sigma 0, I have a bifurcation at alpha equals 0. I have a clear difference of dynamics between this situation where I have one attracting fixed point and this situation where I have three fixed points, of one is repelling and two are attracting. Looks quite different. And then I switch the noise a little bit, and then my theorem says I don't really care about alpha. I have some nice stochastic description, and I have a pullback attractor which is a point. It's a unique point. Okay. So this led so this led that Crowell and Flandely in '98 conclude that there was no bifurcation. So it was said that the additive noise destroys the pitchfork bifurcation. That's the title of that paper in '98. And this was a very important paper, because I think it well worked as some kind of no-go result, where people said, well, if you have noise, you have no bifurcation somehow. So bifurcations disappear in the presence of noise. And so the first time I learned about it was precisely that context. I was interested in some bifurcation in something with noise, and I had additive noise. And someone came to me and said, no. No bifurcation with additive noise. Well known, famous paper. okay, if you say, okay, if that's the case, why not? I think actually the lesson is if someone says something cannot be done or something cannot be true, then you should look into it, so I would say. So that's what we did, because he said, how is it possible that if you have such clear dynamics and I make just as small as possible noise as I like, then suddenly everything disappears. Can't be true. It can't be true. So it's of course a matter of point of view. It's a question like, what is a bifurcation? And so here, the whole question here is like, what is actually a bifurcation? So Carl and Flandry said like, well, bifurcation if you look in the random context, the object here we're interested in is things like the random attractor, Bldg attractor, invariant measure, whatever. And especially this kind of like fiber-wise objects like a Bldg attractor. And said, well, because you can't see a difference at that level, then dynamically there's no difference between the dynamics before the bifurcation or after bifurcation. But if you look at the distributions, then everyone sees that there's difference. So there's another point of view that in the Ireland school they came up with. They say, oh, there's two types of bifurcation. There's so-called the dynamical bifurcation, which is basically measured in terms of these behaviors of these integration of Bldg attractors and the Apollon response and so on. And maybe there's another one which is just in the shape of the distribution. They call it phenomenological bifurcation. Now, this leads to some chaos at that level, because then the question is like, okay, what is actually bifurcation? So there are two concepts which are motivated basically by some one-dimensional examples where they make sense, but there's some problems with the phenomenological bifurcation, for instance, because the shape of a distribution is poorly defined. If I have some distribution and I do a Gordon transformation, I can create as many new maxima and minima in my distribution as I like. Because if I squeeze my space, then my mass goes up in that place. If I take this thing and I just squeeze the space here, then suddenly I get a maximum in the distribution. So it's a bit difficult to see how the shape of a distribution, unless it is some very specific limiting way or whatever, can actually really tell you something about the dynamics. And also in general, I will have a distribution that looks, I don't know, it has 10,000 maxima and minima, and it's a bit difficult to talk about bifurcations by counting the number of maxima and minima of a distribution and to understand something. So the phenomenological bifurcation, although it appeals to the idea that, well, this looks like, you know, around this point we have a nice distribution, and here we have a distribution like this, that looks nice. And of course, in the limit of small noise, these things, they correspond to some sense. But it's not really, it doesn't seem to be really the right or the last words to say about bifurcations in random systems. But the question remains, and I think it still remains, is what is a bifurcation in random system? I think it's a very important question, because people see bifurcations in some practical way. If you have a random system and I change parameters, and people see that at some parameter value we see one type of behavior, and in other parameter values we see completely different type of behavior. Say for instance weather systems. Weather systems, they're measured on climate dynamics. People use random models for that, stochastic differential equations. Clearly, the scientists see different behavior for one parameter value and from another, because otherwise there was nothing to study. But the question is like, if they study these differences and they come to bifurcation theorists and they say like, this looks like bifurcation, can you explain me something about this? Then it gets very quiet. Because people say, yeah, stochastic differential equation, bifurcation, not so clear, not so clear. You can compute distributions, you can compute things, but you, for instance, don't know exactly where is the bifurcation point. And what is the criterion for bifurcation? And so usually, in bifurcation theory, we have a notion of equivalence, and we say that if you change the system in a certain way, and the two systems are equivalent in some sense, you say there is no bifurcation. It's just more or less the same. And then when it changes, being not equivalent, you say, now we have a point where it really changed. So here you see there's several notions of equivalence, like topological conjugates here, so that this system is very different from this one, because you cannot find a coordinate transformation that has this one and this one. It's very clear. But in the stochastic case, this is not so clear what precisely the context should be. Okay. But what we showed to CDLR is a paper with myself, Mark Calloway, and Wanda and Rasmussen, is we looked at this carefully and we noticed that actually there are some differences with these random attractors. Namely, there are properties of attractivity which are different. So, like in the first lecture, I had a random attracting point, which is uniformly attractive. We know that all neighborhoods around this attracting object shrink by a factor of 1/3 always. So it's exponential decay with a fixed rate that's uniform. So everywhere, always, irrespective of the noise, we have the same shrinkage. But in the and this is the same thing that happens here. You see, we have a just contraction of the flow, and we have exponential uniform behavior. So let's try not to read too many things. So there's a certain key thing that the convergence rate to the attractor is of this form. This is the Lyapunov exponent. So we have a constant times exponent lambda t. Sorry, the lambda should be negative, so not minus lambda t. Okay, so we have a convergence exponential, and so the Lyapunov exponent gives you this kind of formula. But the whole issue now is that whether or not this constant here is uniform, not depending on the noise, or whether it is depending on the noise. So in the first lecture, I had an example where this constant clearly didn't depend on the noise because we always had the same rate of convergence. So uniformly we get contraction. But it turns out that in this situation, we have a transition between uniform and non-uniform contraction. So yes, here things have the Lyapunov exponent and we get contracted, but the constant in front of this term here in the formula depends on omega and is not bounded by anything. So it means I can find some realization of the noise where k is as large as I want.
Didn't you say in the previous slides, didn't you say that the random attractor is a singleton and it uniquely exists?
Yeah.
So how can, and it doesn't depend on alpha. So how can this random attractor depend on alpha? Isn't it the same as...
No, so it depends on alpha where it is, but it's still always it's always a unique attractor. For each alpha, you have a unique random attractor.
Okay, so in fact the random attractor in the previous slides also depends on alpha.
In some, yeah, because the whole equation depends on alpha.
Yeah, okay.
Yes, sure. So the specific, of course, the specific, yeah, of course, because this flow depends on alpha. It will depend on alpha, but the result.
But it's a singleton.
It's a singleton. Yes. So what I'm talking now about is about what are the attractive properties of a singleton point. Okay, so what I'd like to do is to explain this in terms of two-point motions, rather than doing the analysis, which is also possible. Maybe we should first have a quick break,
okay.
And then another 5 minutes or so.
So 5%.
Yeah.
자, 11시 5분.
So I little movie here going on. I want to show you, but this is actually a two-point motion of the still double well thing, and you see here how the synchronization happens. So I think sometimes a picture does more than many formulas. So you see a little bit what happens here. We have very steep walls, and so if I start with 2 points in different places, and of course with small noise they will just stay separated for a while. But what happens is that when you have large enough noise either to the left or to the right, they get pushed into one direction. And when they get pushed in the one direction, they say they come in the same well. Then they exponentially come closer to each other. other, and when they're very close to each other, it's very difficult for them to separate. Because when there's a noise that pushes them this way, very quickly they would actually just push both to the other side. And the only way to separate if they will come very close to this point, and they can basically separate across from there, but the chance gets smaller and smaller. So the aspect of having this maximum here is precisely key to this non-uniform attractivity, as I will explain. So maybe let's explain the words first from the picture. So when we have a convex potential and everything goes downstairs, and we have a uniform attraction because we just have basically one well to deal with, and the only thing that the well does, it makes us contract. That's the nature of this well, is the gradient dynamics. In this case, we have contractions here and here, but here we have actually expansion. If I take two initial conditions here and I switch off the noise, the points, they tend to separate. So when the distribution sits over an unstable region, that means that there's always a possibility that my points come to a region where somehow they actually separate for a while. Now I can do an experiment, thought experiment, and say like, look, maybe I converge eventually, but can I delay my convergence to synchronization, or can I desynchronize? So you can see if you could choose the noise, I can actually, if my points are together synchronized, if I could be devious, I could push the points to the noise to the right position and just let go, and then the whole thing would fall down. They would separate. So it would be possible to choose a positive probability set of realizations of the noise that pushes me to a situation where there will not be no synchronization. Now, the name of the game is that in the time to infinity limit, I will lose that game. Because what happens is that my probability gets smaller and smaller, goes to probability 0 at the time infinity if I want to keep doing that. So that's why, for full probability, I will synchronize. The problem is I cannot predict how long it will take, because I can take this, if I say for 1 million years I don't synchronize, I can do that. It's fine, it's fine a probability, no problem. And for 10 trillion years I can also do that, but not forever. So this is a good warning also against these mathematical limits. You say, I take something time to infinity. Really, this is not a harmless limit. It's there where you suppress some of these phenomena that have that could really happen. So the fact that we have synchronization to time to infinity does not mean that we have uniform synchronization. And we can actually have very erratic dynamics. It just depends a little bit how easy it is to find a region where points separate. But in principle, it could be that, for instance, that the chance to separate at every step is like 99%. That means you separate a lot, but the chance to not separate 1%. If you now kind of accumulate that, then this 1% will win it in the long run, the 1% of never separating, because you go to the next event and it's again 99.1. Everything condensates at some point in a situation that you're all synchronous. That's kind of important. Yeah. So if you do two-point motion, that's what I wanted to do. You can also see this very clearly. So I'm plotting x against y, two particles, and I just use the diagonal x equals y. That's the one particle motion. So if alpha is smaller than 0, then I have a stable equilibrium solution. And, well, actually, the stable equilibrium solution will be stable here, but it will also, we have the invariant lines here, that will of course also be stable there. So you see that we have a globally stable object in this space, but we know that, of course, that's just the equilibrium solution. Now, if I have some noise, what's the noise doing? The noise acts, because we have two times the same system, we have x, y, going to this one. So we have two times the same realization of the noise. That means that my noise acts always in the diagonal direction. As I saw this last time yesterday as well. So the noise So we get a picture where we have this attracting object, and yes, we oscillate a little bit in this direction, but not much happens. So what we get very easily, we get some kind of attraction towards the diagonal, because we have exponential convergence just because of these eigenvalues here, and then the noise keeps moving me along this diagonal. So I get the exponential convergence to the diagonal as uniform convergence. But the situation is quite different if I have the extra point. Now I have an unstable point and two stable points. So this is stable, stable, unstable, unstable. So maybe remember from yesterday, now we can make again a grid because we have invariant lines for the flow, for the deterministic flow. Right. So we have lots of arrows here. Always the same game, it's not so complicated. Just to make any mistakes. Okay, this is nothing, but this is the boundary. And so we have these 9 equilibria. You see this one is stable. And these ones are stable. This one is very unstable and they have some saddle points. Okay, so what's the kind of behavior? So here's the diagonal. So I'm contracted, say, to such an area like here. But then by the noise, what can happen is I can come to this unstable point. This is the top in my thing for my two-point motion, and then I can go here. But if I'm in this region, I of course also have the opportunity to basically escape. Why not? For instance, if I choose my noise in such a way that I just go precisely to this point, and I just let the noise switch it off, then from here it would just flow into here because I'm in the basin of attraction of this stable equilibrium. So with the now of course this is open, so I can take a finite probability that I end up here, and then I let go, and still find a probability, just a very small noise, and it will flow to here. Because I become unstable. Now from here, then again there's also a probability easily to get escape from here and then go back here. Actually it is difficult to stay here. Even though it's stable, but the noise is more easy to escape from this one than from that one. From this one. From this one it's easier to escape than from that one. So you have a cycling mechanism. So you can see here that this, in the picture, what I described, that the points go and they separate precisely in this picture to go from the stable point to an unstable point, and then say let go. So you can see from this geometric picture, I can immediately see there's a positive chance to separate always. If I'm wherever I am, because when I come to the diagonal, I never sit on the diagonal. The diagonal is invariant, but at best I exponentially come close to the diagonal. But if I'm not at the diagonal, I can always end up in this region, which is unstable. Why not? If my density sits on the whole, if my density, okay, if it separates the two pieces I count, but if it sits over the whole thing, there's always a chance to come there. When there's a chance to come there and I switch off the noise, because I choose the noise realization the appropriate way, then of course I can escape. And this precisely gives me this problem with the constant. Doing this game, I can make this constant k of omega as large as I like. And so the tricky bit is to understand why, in fact, this actually still leads to an asymptotic zero chance. Yeah? But this is precisely the game. So this is actually the height of the synchronization argument. But rather than do these formulas, I think it's nice to look at this picture. So you have geometric. So this is an example maybe of doing a geometric analysis of stochastic dynamics. Sounds a bit strange because I'm drawing phase portraits of the things without noise. But you can really, from this picture, because you don't know what happens if I add the noise. If I can switch off the noise and make the noise very small, then make the noise very small, it looks very close to the dynamics here. And if I make this noise large, I know I can make excursions which are very far from where I am. Okay. Good. So this explains some things. So the conclusion then, somehow, is that we do have a bifurcation. But we have a bifurcation in loss of representativity, but also bifurcation in behavior. In this case, I have no chance to escape from a synchronized state, ever. In this case, I have always a positive chance to escape from a synchronized state. Now, you can't tell me that it's not a different dynamical behavior. This phase portrait is completely different from this phase portrait. Yes, they both have a random attracting fixed point as an asymptotic object. That fact hides the fact that the underlying dynamics is quite different. So the title of the paper of Carl and Vanderlee is Additive Noise Destroys a Pitchfork Bifurcation. I have given talks in the past where I say additive noise does not destroy a pitchfork bifurcation, just to make the point. Of course, the whole question is like, in what kind of aspect are we interested? If really the only thing you're interested in is your Poincaré factor, but it's a singleton or not, of course, then you would say, from that point of view, there was no bifurcation. There are many other points of view you can take, where it's clearly that there's some different aspects of dynamics. So the bifurcation is a fluent terminology. If you study it, for mathematicians that's difficult because in every context it has a different meaning somehow. So because but it is important to address a certain appropriate sense of bifurcation that means something to the people. So the change is a qualitative change of the dynamics in some sense. And my claim is that obviously we have a qualitative change of the dynamics. So this saga has a tail, and here let me. So in the meeting in 2 weeks' time, we will be meeting here, and I hope to see many of you there as well. Martin Rasmussen will talk about this problem in somewhat more detail. It's about conjugacy. So in bifurcation theory, especially in low dimensions, there's a popular way of classifying dynamics by saying two systems are the same if there's a coordinate transformation that maps one system into the other system. And they say that even only that's the equivalence relation. So bifurcation means that you have a loss of the opportunity to transform one system into the other. Okay, so in the non-autonomous context, what happens if you do coordinate transformation this way, it will have to depend on the noise realization or on time, just because of the skew product. So it's not the same transformation; it's a transformation that depends on omega. One has to be applied at omega, and the other one at that the omega. There's no other way. So you ask for such a conjugacy relation. And you ask, does there exist an H which is invertible and continuous? And if so, you would say that gives me an equivalence relation between systems. And so famously, for instance, people have proven what's the name? I've proven that the saddle points are, for instance, all saddle points are equivalent on conjugacy. Good. So the theorem with Son and Martin is that in the pitchfork example, with alpha small, but probably it's also true with alpha larger, it's actually true that the dynamics is topologically conjugate. So the fact that you have just a singleton is actually enough to create this conjugacy with such a omega-dependent transformation. So this is contrary to what I just was claiming. So if I say that having a conjugacy is, if you have a conjugacy between two systems, there's no bifurcation, they're basically the same system, then it basically says that this system is the same as this system, because the orbits of this system are conjugate to this system in a rather complicated way. But now what's important is that now it happens that it actually then depends on the regularity of this transformation. So yeah, it can be invertible, but it then depends how it depends on the noise. So you see that if you have a problem with that the noise realization gives you different rates of attraction, then you could see that maybe there's a problem if you have some kind of equicontinuity, if it's too regular. So if the conjugacies are regular enough, if they kind of then somehow you can't do it in a very natural way, because you actually know that you can't change And this is actually referred to some other things that you actually can't do it. So it's true that on a wild class of coordinate transformations, just continuous coordinate transformations that are invertible, you can do things, but if it's some more regularity in terms of the noise dependence, then you can't do it. And this has precisely to do with the fact that this K of omega blows up. So now the good question is like, so maybe a reasonable definition of conjugacy would have to do maybe with that you cannot just ask for any invertible transformation, but maybe the transformation has to be nice, like equicontinuous, in a good sense, with respect to the noise realization. So these are just raising questions on this exercise and what is actually a reasonable thing to do. And so there are different points of view. I think it's completely clear that we have different dynamics, but it then asks a question about whether actually the notion of conjugacy is a useful one. Because if you can transform a chicken and a horse into each other by a conjugacy, then there's something wrong with your type of conjugacy in some sense if you see that the chicken is not equal to the horse. So this is just a challenge, I think, and we have to get still work with. Okay. Good. So this was basically what I was saying. Okay, I want to kind of go through another example that's basically is also an SE example, which just gives you another variation on the theme. So there's some similarities with the model here, but also maybe has an appealing application. We can learn something from that. And after doing this one, which I will do relatively quickly if you bear with me, then I will say something about high dimensional examples. So first of all, I'd like to re-emphasize that the dynamics we see here, and we saw in the previous lectures as well, of a random equilibrium point is nothing to cheer about. It's nothing to say like, hoo-hoo, great result, because it's the same thing as an equilibrium point for an ODE. So to prove that we have certain classes of ODEs where all solutions converge to a single equilibrium point is not really a great achievement in dynamical systems. And we have, this was of course at some point a great achievement when people designed diagonal functions and all kinds of things to find unique equilibrium points. And there's still some branches of science where people really like to find unique equilibrium points for their models, because they believe they should be there. But we now understand that we have much richer dynamics. The issue is when we add noise, that in order to start understanding something, it seems to be a good idea to first understand the simplest type of asymptotic dynamics, the simplest type of attracting object that you can find. And the random attractor, the random attracting fixed point, is basically the simplest one you can imagine. It's unreasonable to assume that if you have noise, that unless the noise is zero at an equilibrium point, always, that actually you would have a normal equilibrium. It's not a strange. It would be a very strange noise in the system to allow for a real equilibrium to exist, because it's a non-autonomous system. So you shouldn't have a system which just sits there. But a random equilibrium is the simplest type of asymptotic solutions you can find. So we're looking at systems that have this very simple behavior. Like if you have an ODE in one dimension, everything converges to an equilibrium point. So our results here are basically equivalent to that type of result, in some sense. And the challenge, of course, are like what more is there to develop. The problem, though, is that if you don't even understand the equilibrium point, then maybe we should spend some time on the equilibrium point. This is what we have been doing. Okay, so we now look at a slightly different model of, it's a model for stochastic resonance. Stochastic resonance is a phenomenon by which people see a strong response to noise in experimental settings. It's very famous in physics. People use it all the time. It goes by, in different applications, maybe even different phenomena are all called stochastic resonance. And why was I interested in addressing this problem of stochastic resonance? Because you'd like to do something with stochastic dynamics that maybe appeals to something interesting with stochastics in physics. And stochastic resonance is the most famous phenomenon in physics with some stochastic in it. And the idea is that you have some phenomenon, and when you drive it with the noise, you get a really strong response from it. You get enhanced behavior in the system just through driving it through noise. That's strange. You think if you add some noise, it will lead to blurriness. No, it will actually have a pronounced response in the system. So we here have a very simple system. It's again a double well. And the question is like basically, how does the dynamics in the double well respond if I oscillate the well by an external force. So we are interested in how does the dynamic respond to oscillation. Of course, what we'll do is we then have also a noise term that we take as simple as possible. So we just make additive noise. That's a toy model. It's not presumed to be super applied, although people, of course, take it kind of serious already for many years as a model. And the question, like, what happens if we change the magnitude of the noise in such a model? And so let me show you that this model without this guy, A equals 0, is the same model we just have looked at. Right? I will take A to be positive, so we have a double well. I'm not so interested in a single well. We can vary here the amplitude of the driving, and we can vary the amplitude of the noise. Okay, so here you see some examples. So alpha is set to 1. In the example, I think A is 0.12 and W, so omega, the frequency here, omega is 1,000. So we have a lot of iterations here. So you see here the oscillation of the signal is a sigma omega t. That's here. You see here the signal of the dynamics, just the orbit of the dynamics. And here's a histogram plotted of where the points are. Just accumulating the histogram. So we see something is familiar. We have kind of double hump distribution. Looks a bit like the stationary distribution we saw before. And we see, of course, some interesting behavior here. So here we have behavior where we seem to kind of stick around a very long time in one well, and then at some point we jump and we sit a long time in the other well. So these are the two wells where we can sit. So this picture you have to think of twisted around. This is the left and the right well where I can sit, and this is the time series. So this is the right well and the left well. But here you have a system where the signal oscillates kind of in resonance with the driving. You see that there is a fake line here, oscillation, which is this term. You see here this term now basically oscillates basically with the amplitude of the thing. So this is basically stochastic resonance. I drive at a certain frequency, and I don't do anything else than actually adding more noise. I increasing the noise. Here we have low noise. I don't really see so much this oscillation. I add more noise and I see oscillation. If I then add more noise, I see almost nothing anymore. It's just lost. So this enhancement of the periodic signal through a resonance to stochastic input is called stochastic resonance. Okay, this is just a simple term model. Now, our question was, can we understand the dynamics of this system in terms of, not just in terms of some signal or in distribution, but in terms of the dynamics? So the thing is what we so the result is that there exists a unique global attracting so-called random periodic orbit. That's a question you know, yes, I do we have random periodic orbit. So there exists here a random periodic orbit, and this is an atom. So we have a random point, which is a tracker. It depends on the noise, but it also depends basically on the time variable, tau, which is an augmented time variable that measures the driving, and it has the property that it basically is time periodic with this behavior. Okay, so associated, we can plot certain histograms, some functions. So the one that we just saw was this one, where we just integrate over the set of all time, and we just kind of we plot a certain histogram of this time. I call this rho bar p, and this turns to be some kind of some double humped distribution, very similar to that of the non-driven system. But there's also another object which you can sample that I sampled precisely with the driving frequency. If I sample with the driving frequency, we see a periodic. So we have a periodic stationary measure in some sense. It's a time-dependent. Well, it's not a stationary measure clearly, but it is something like it. But because I just take this histogram, but I just take the sampling frequency Right, and if I take the center frequency, I see precisely a periodicity as a function of tau, which is basically the point at which I take the return map. And then you see an oscillation, for instance, where everything sits in the left well, to everything goes to the right well, the left well, the left well, the left well. So these distributions are related precisely to this periodic point. So how can you, for instance, test for such a thing in a signal? So suppose I see a double well, I can look at power spectrum. This is a, but I could also just look equivalently. I could take a sampling frequency and I could scan for sampling frequency and see whether I see the same distribution. So what would happen is that you see always the same distribution, unless you see always the row bar, unless you choose T basically is the driving frequency. If you choose the driving frequency, because this guy, if T is if I take T plus epsilon here, it will also converge to rho B. Because if I just take it off the period, it will sample in a quasi-periodic way all other times as well. But if I choose precisely in resonance, I get a very nice resonant behavior. So we have a system here which has such a structure. It has also this one-dimensional setup. So this is just so it should be. So I will say something about the structure there, just for theoretical purposes. But it's important to say that actually the structure of this dynamics gives rise to trying to understand what the stochastic resonance is. But the numerical values really make a difference of whether or not you have this effect. It's not a topological effect whether we have the oscillations or not. So this is what we call the resonance regions. You see that you oscillate roughly in line with the signal. Here you oscillate with the C, and here you clearly don't really oscillate with the driving frequency. But it's not a topological effect. So you can't really see it from dynamics, but you can derive it. You can derive a measure, an observable that can tell you whether you're at resonance or not from dynamical observations. So the classical measure of stochastic resonance is basically look at the average position within the distribution and to see whether you have a stochastic resonance. So you take, you look at these T, you look exactly where you have a maximum for the amplitude for this. So this is the expectation value of the position, and you say so if you oscillate a lot wide. So as I said, this has something about the amplitude. This is basically the amplitude of the oscillation on average as a measure of resonance. But that's not. But this is just more like a static distribution. So you look at the amplitude of a static distribution, and you hope that it means that it oscillates. But if you know about this dynamics of the thing, you can also compare the mass to the left and the right before and after the oscillation. So if you look at these pictures, you can compare the mass to the left and the right. And then we know that if we go from this picture to this picture, we know that we have a transfer of mass. So some orbits must jump, otherwise it's impossible that all the mass changes. You cannot go from this picture to this picture without any particles jumping to the other side. So it seems to be a better measure to look at these measures and to compare them. So we found a different way of doing that. So we compare basically the masses on either side and normalize it in a certain way. And then if you multiply the numbers by each other, then we get a lower bound for the probability for a particle to move from one well to the other one and back. And this seems to be a reasonable number which really has a dynamical meaning. It's really some kind of guaranteed rate at which we oscillate, and that's basically what you want in a resonance. Now for the specific model, we calculated this, and it turns out that it doesn't make so much of a difference. So there's one here, the X bar has a maximum at a certain level where we also numerically observe this phenomenon, and our measure P also sits near this maximum. But I think an advantage of this way of looking at it is that we have a more dynamical way of looking at it than in the other case. Anyway, but then another interesting challenge is to look at these non-autonomous random system. So in a random system it's non-autonomous because it depends on noise. But the noise, of course, has some independence and so on and so on. If I now have a signal which is not independent, deep throat, then of course I can try to separate two types of signals. One maybe is a trend, and the other one is something which is independent. So I can hope that my signal is something noisy that I like, IID, plus something which maybe has a trend. So my differential equation, which had a dWt, but also an A cosine omega t dt, and we have two types of input. 1.1 pi is just depending on time in a deterministic way, and one is. So this is basically an IID type thing. This is not. Yeah. So this is important. So by separating it, we want to treat it in a different way. So you can do that by enhancing the co-cycle in some way. You enhance it with an augmented variable that measures the time over here. It says basically, if I start at a given point in time, my equation has different values here, and I treat the noise in a separate way. So I enhance the co-cycle with an extra variable. So what happens here, so usually I map into X the time, noise, and phase space, go to phase space, but now I have an extra time, and this time basically measures where I'm sitting in a non-autonomous way. So in general, you can do that, where we so you have this formal thing. You have this co-cycle with an extra variable tau, and tau says basically what my starting time is in this non-autonomous system. And in the special case, if you're periodic, of course, you will have that these operators are the same when it's tau, or tau plus capital T, and capital T is the period of the driving, because I come back and have the same structure. So the same thing that we did yesterday and the day before, we can also do for these kind of systems. So we can augment this picture and work with some kind of non-autonomous version of Markov operators, non-autonomous versions of pullback attractors, and so on and so on. So I have also non-autonomous versions of, so tau is the reference time, non-autonomous versions of absorbing sets, and so on and so on. So this can be done. Maybe with the time I shouldn't say to myself. So what I wanted to show is basically that this can be extended. It's maybe not such a surprise. And in a transparent way, this theory sets out that this is an attracting domain. We usually have the A of omega. Now we have A of tau omega. The tau ranges from 0 to t. Okay, so maybe here I say something about the absorbing set condition. So here are some conditions. You see there's some disputivity and integrability conditions that I use to prove that we have an absorbing set. And without going into details, because it's a bit technical and it's analysis in the sense that you just, it doesn't always work. It works for some classes of examples. The trick is somehow, the standard trick in these kind of problems is to work with reference to so-called Ornstein-Uhlenbeck process. And what you do is you compare the dynamics with that of an Ornstein-Uhlenbeck process, and in that sense you get so this is the Ornstein-Uhlenbeck process, just a linear SDE. You compare the signal of your SDE with that of an Ornstein-Uhlenbeck process, gives you another one, and by magic somehow this is the equation that you get for this Z is manageable in some sense if you have the good conditions to show that you have an absorbing set. So it's a bit tedious, and who knows, maybe someone finds one day a better way of doing this, but most examples that are known where you can actually control absorbing sets is like this. So you get some kind of differential equation for Z, and it depends now, it's now a random differential equation. So in terms of stochastic differential equation has a reference to an unknown, to get an abstract noise or a Wiener process. And a random differential equation has a reference to an explicit incoming signal in the ODE. And in some sense, where we have additive noise, of course, we also got the form of a random differential equation, because then we also could explicitly integrate. But if we can't explicitly integrate then we don't call it a random coordinate differential equation, RODE. Anyway, but then you can actually, the bounds that were given and the integrability conditions that were given in the theorem, so these conditions cannot be used to study this differential equation with some inequalities, and to show that you indeed have a absorbing set. So that's quite technical, and so what makes it work is that if you have steep enough behave towards infinity, that gets really drawn in fast enough. So the idea is basically that if you have this infinite system, the diffusion can throw you out, but if your incoming the pool insert is stronger, then the diffusion can throw you out. Then actually, your mass will not really fly away. It will actually stay in a bounded region, basically. Okay, good. Yeah, anyway, but in that sense, kind of we can show. So we have similar objects as before. We have an A. We used to have A omega as a random fixed point, but now I have an A tau omega. And if I can show that that's an atom, then I have a random point, because now I have a point that also is labeled with tau. So you can also think of tau in the periodic sequence as like a punctuated return map. So you think you have a time periodic system, and I just fix the time and I wait till the system comes back. Then I have a basically discrete time system, and the discrete time system then will have a random fixed point. It's discrete time. And then when I can look at the reference time, and I can really complete this into a so-called random periodic orbit. That's another point of view where you can prove most of the things also in this thing. So there's some kind of open questions of this. There's here some things that we can do these measures. We can do stationary measures. We can disintegrations. We can do periodic versions of them. It's not so. I think for the sake of time, I should really not spend too much time on it. I just want to show that you can actually also treat a time periodic thing with this, and you get similar kind of behavior, and you can have an augmented picture. So we get this integration formula again now depending on tau. If you fix tau, you can again do the same disintegration that we did before, and we get this kind of A omega set as a section and so on. And we get similar kind of formulas here, for instance. If the flow acting on the disintegration from tau omega, then it flows forward the tau as well as it pushes forward the noise. Just a reference time. So it's just a geometric construction. And then such a kind of periodic, if you have a periodic, the invariant disintegration, that's then a random periodic orbit basically. But you see that the period comes from the driving. It's very, so it's natural to have a random periodic orbit in a non-autonomous system that is periodically driven. Because there's some kind of like, it's kind of semi-autonomous in some sense. So because the time T map is actually autonomous, it doesn't depend explicitly on the time. But it is not, it seems to be kind of quite unlikely that you see periodic orbits, like in deterministic dynamics you see periodic orbits everywhere. But in stochastic systems, it seems to be very hard to find periodic orbits. But maybe if you have these oscillating domains, you can see something like that, but otherwise, not so much. So it's very peculiar related to these things. Okay, you can set up also these Markov operators and so in this non-autonomous way. Anyway, the result is that we have a stationary T-periodic measures and T-periodic objects, and basically we generalize all these things up to the fact that we have a random periodic orbit for this driven system. So it looks very much, these systems look very much alike, and of course we have the same kind of issues, and of course also here we have an attracting periodic orbit that is not uniformly attracting in this resonance example. So that's the same type of problem. But still is an open problem here. Is, for instance, if you take this drawing, this driving not periodic, so the periodic driving is very special. We know how to do a periodic things because we can just basically go to the period now. If you have, for instance, quasi-periodic driving, not so clear at all what happens. So if I take two frequencies which are incommensurate, then I can't really play these tricks so easily, and it's not so clear what I can do. let alone if I take an arbitrary signal here, which is non-autonomous, but is not recurrent in any obvious way. So this becomes very, very challenging problem. But I think there's an interest in random systems that are also non-autonomous, and it would be interesting to understand. So non-autonomous systems are hard to understand in many ways, because the equations of motion depend on time. But I think that the world is like that, so the world evolves and nature evolves to be just not all stable, always the same. So there is a certain need for understanding of such non-autonomous systems, and also non-autonomous systems with noise fall under that. So it's good that one can probably generalize those things. Okay, I want to spend the last few minutes on what I call more interesting dynamics. So I've been not boring you hopefully, but I have basically been bombarding you with attracting fixed point, like the attracting fixed point is the only thing that's there. And the truth is, I think the attracting fixed point is the only thing that is understood. And apart from that, very little is understood. Really what one should be interested in is like, is it possible to have something else as a random fixed point, and what would it look like? And what does it mean for the dynamics? So let's look at some examples. This example that we studied with Maximilian Engel and Martin Rasmussen, and those previously studied by Young and Kevin Lin. And it's just a very simple model of a limit cycle. So this is a equation on the cylinder. So theta is 2 pi periodic, and y is just like, so we're sitting on the cylinder, and we're interested. We have a limit cycle, and we're interested to understand what happens in such a limit cycle with noise. So the limit cycle here is stable, it's alpha is positive, y dot is minus y, it's stable, so y is this direction, and this is theta. Yeah, and this is my limit cycle, y equals 0. It just goes around. So the question is like, what happens? So if you have a system like this, so here we have a noise. I have here a dependence on theta, and the question is like, what happens here if I drive up the shear? So what's the term B do? If B is 0, then basically everything just drives uniformly. So the fibers basically keep on straight. So what happens if B increases, then you have some tilting of lines, so we have shear. So if you flow a thing with shear, then this guy starts tilting. That's shear. That's the term B does this. So term B does it because it's depending on the height of y, the frequency with which theta rotates goes faster and faster in a linear way. So we tilt over. So it was observed by Young and Kevin Lin that if you have a stochastic system and you increase shear in such a way that you actually see numerically, you see a positive diaphragm exponent, and that's something that we in the paper actually managed to prove, which is not so easy. For a special case, that this function has a constant derivative almost everywhere, in which case you can actually analytically solve it. But I don't want to talk about that, and I will actually talk about it in this meeting. I won't give a talk where I will talk about that result. Let's just look at phenomenology. So if you compute the diaphragm exponent, then you can see that as a function of sigma and alpha, but sigma is actually commensurate with B. So whether you increase sigma or B is the same for this model, with the coordinate transformation. That you see that you have some behavior where we have negative exponent. This is the 0. This is lambda, the top exponent, the diaphragm exponent. So this is 0 exponent. And if you're a negative exponent, then everything on average contracts. But if you have positive exponent, then there is also some expansions. You see here that in this model, if we increase the noise, or equivalently decrease the shear, then actually we tend to get in regions where we have positive diaphragm exponent. And so the question is, what does that look like? And so here's an example of construction of the pullback attractor, mu omega. So we numerically simulate until we get something which looks like a stationary measure, just empirically. And then what we do is take the pullback of this object to a certain time. So if t is 0, then pullback t is 10, t is 50. And this is in a region where we know we have negative outlook exponent, and you see in this model that we basically get attracted to one point. And just numerically compute pullback attractor for the stationary measure that we also get numerically, and we get a point with negative diaphragm exponent, which fits with our previous idea that negative diaphragm exponent plus some good conditions, which apparently are satisfied, gives rise to attracting fixed point. But here's a case where we have a positive diaphragm exponent. And so here this is a picture of numerically obtained approximation to stationary measure. And then when we move it forward, something completely different happens. So we don't see any convergence to a point. To see convergence to something that looks like some kind of somewhat strange object. And so these objects look very much like strange attractors that people see in deterministic systems with positive diaphragm exponent. So you have an attractor with positive diaphragm exponent, and you see things like this, and people interpret these things, for instance, in terms of that an invariant measure which sits on an unstable manifold associated with positive diaphragm exponent. Now, I think this is very interesting. So we have a transition from something where, by changing a parameter, we had an attracting fixed point into something which is like some kind of quasi one-dimensional object. But this is very poorly understood. So it's not, I think, even statements about to what extent where this measure precisely sits on is not so well understood. There's of course some results by Lassagne-Young and Bldg already from some time ago, which has some generalities, but it's quite unclear where this thing precisely comes from. And so the challenge really in random dynamical systems is not just to understand where we have attracting random fixed points, because that's the equivalent questions like when can we find the Laplace function for an ODE so that we have a unique attracting equilibrium where everything flows into. That's of course of limited use, but the challenge is to understand beyond that. So what other things can happen, and how can we describe them, and how can we do something with them? So another nice example is that of stochastic Lorentz models. We have Lorentz equations with some driving, and this was used by Michael Chakroun in UCLA and Simonette and Michael Gill who work there on climate models, and they like to also use a dynamical systems approach to some extent. And they did some numerical simulations of this invariant measure you see for the Lorentz model, and this is here a snapshot of mu omega for some omega. But you can of course also look at we can look at mu omega in a complicated situation, but then we can also of course look at the mu omega of theta t omega. We can look at this object, the pullback measure. If you flow forward in time, it's like you reference time, go forward, and you follow what happens through the time. So this gives you some kind of like dynamical picture of what your dynamical attractor, the time-dependent attractor, somehow looks like. And so there's a movie that I want to show, just as some kind of motivation maybe of what can be done. So people they think that science should be motivated by pretty pictures, and this is maybe one of them to convince some people. So this is a time evolution of the random attractor, which is not a fixed point in the driven Lorentz system. So black means that you have basically a low density or zero density, and bright color is high density. And so this is some kind of somehow the equivalent of a chaotic attractor that you have in the deterministic dynamics, but then for a stochastic system. And the question is like, how can we understand those things? What are they made of? Why are they there? And what can we tell about them? So this is systems. So despite me talking all the time about random fixed points, the challenges in this kind of thing, but the random fixed points are still, there were still some small challenges. The problem is, of course, there's some technicalities which are not entirely trivial, but yeah, so it's a field which I think is in strong development, and there should be lots of opportunities for working in this field. Also in relation to applications, stochastic models are very important for people in application, increasingly so. And I think techniques we can develop to understand even toy models could be very useful for people with real-life applications or even data analysis, so to make some kind of sense of the world that they see. Okay, thank you very much, and see you tomorrow at 10 again.
Yeah, thank you very much.